Hello. Welcome to this overview of SmartEP Cortical Auditory Evoked Potentials. Specifically, we will be reviewing the postsynaptic potentials middle latency response, or MLR, as well as a 40 Hz steady-state response typically used for threshold estimates. Then we will cover the late latency response modality, or LLR, and dive into options available in the SmartEP P300 MMN add-on module. Finally, we will review the generation of CAEPs using the Acoustic Change Stimuli Paradigm, which produces the Acoustic Change Complex. There are many reasons why you would want to acquire cortical evoked potentials. For starters, CAEPs provide neurodiagnostic perspective across lesion types. Site of lesion testing is important because when combined with ABR, a clinician can differentiate brainstem from thalamocortical involvement. The MLR has generators around the inferior colliculus through the cortex. The CAEPs, as the name implies, is affected by cortical and subcortical areas rostral to the brainstem, with contributions from auditory and frontal cortex, and affected by the reticular activating system. CAEPs can be used for frequency-specific estimation of hearing sensitivity or audibility in cooperative children and adults. When evaluating young children, keep in mind that CAEPs are affected by age and maturation development. They provide a measure for central cortical deafness diagnosis. They can be used to assess higher-level auditory central nervous system function. For example, in adult functional hearing loss cases, or objective verification and compensation cases. Clinicians can monitor the maturation of auditory central nervous system cerebral function, such as in auditory neuropathy spectrum disorder. CAEPs provide information for neurodegenerate diseases such as MS, Alzheimer's, and Parkinson's. Clinicians have used CAEPs for neurodevelopmental assessments and can also provide insight into the impact of hearing aid use and pre-implant assessments. CAEPs have been used to assess adequate stimulation in children and adults with cochlear implants and hearing aids. They can also be used to assess stroke victims and closed or mild head injuries. Trauma-related cortical dysfunction, as well as recovery and plasticity post-injury assessments, can be obtained with these measures as well. And finally, these tools can be used to assess characteristically exogenous and endogenous cortical responses in order to evaluate sensory gating and the brain's ability to discriminate between stimuli in attentive and inattentive states. To acquire the CAEPs with the Duet device, you will need standard supplies such as skin prep pads to prep the electrode sites, the 5 electrode lead patient cable, reusable gold cup electrodes or AMBU disposable cup electrode leads. These will be used with 1020 conductive paste to adhere to the patient's skin and will be affixed to the patient with surgical tape. The electrodes are placed in a typical 2-channel setup for right and left hemisphere data acquisition. For several CAEPs, temporal and central international 1020 electrode placements might be of interest. The images on this slide show the connections for the Universal SmartBox platform, as well as the connections for the Duet 5 electrode lead patient cable. The test ear electrode positions, which are typically the earlobes, are always connected to the negative inverting input for each channel, where channel A is the right channel and channel B is the left channel. Use CZ for the positive non-inverting electrode, connected via Y adapter to both positive inputs on each channel. Low forehead is connected to ground. If you will be monitoring the eye blink artifact, then you would connect the recording electrodes to the appropriate channel and then use the second opposite channel to monitor the eye blink by placing the positive and negative electrodes above and below the eye, respectively. The preferred stimulator for the acquisition of CAEPs are the insert earphones. Being mindful of possible artifacts. When testing persons with hearing aids or cochlear implants, sound field speakers can be used to deliver the stimulus. IHS offers the following components for sound field option. The Duet or Universal SmartBox sound field output cable to amplifier is used to connect the Duet or Universal SmartBox to the sound field audio amplifier. The speaker cable connects the sound field audio amplifier to the speaker. Note that the calibration of the stimulus files is affected by the distance from the patient to the speakers. The sound output level will affect the latencies of your responses. For additional information on sound field setup and calibration, please contact our support team. The testing environment should be shielded and must be properly grounded. A soundproof room or booth is recommended. Please refer to IHS's techniques for acquiring good quality AEP recordings video and to the Isolation Compliance Smart Note for additional guidance. Patients should be tested seated or lying down on non-conductive surfaces or recliners. Patient state is important and should be as controlled as possible. CAEP testing should be performed in awake patients. For awake patients, a silent movie can be played on a tablet-like device, preferably mounted on a wall or stand away from the patient. Patients are asked to refrain from any head or body movements and to minimize eye blinks. There should be no talking during the test, and the patient should focus solely on the movie being played or the task being instructed. As P300 testing, for example, will require the patient to be alert, attentive, and count the oddball, uncommon, rare stimuli. If the tablets are used and will be held by the patient, then they should not touch any electrode leads during testing. If connected to power, tablets require a 3-prong grounded power supply. If the tablet does not have a 3-prong grounded power supply, then it should be fully charged and run off of battery in order not to introduce any electromagnetic interference. When ready to begin testing, enter the patient's information into the IHS testing database. Check impedance and then follow this simple 3-step acquisition process. 1. Load settings and select a pre-saved user-defined acquisition parameters settings file. Then 2. Select the test year. And 3. Click Acquire to begin collecting data. You should always begin with the gold standard in auditory evoked potentials and acquire a standard high-intensity click ABR, for example at 80 dB NHL, to verify neural synchrony. Next, moving along the auditory nerve, we will explore the Middle Latency Response, or MLR. In SmartEP, the modality to acquire the middle latency response should be set to auditory MLR. This is typically saved as part of the settings file. To load a pre-saved user-defined MLR settings file, either select the protocol menu and choose the settings option to open a selection window, or click on the Load Settings button on the control panel and load the MLR.set file. A typical MLR settings file would be programmed as follows. Stimulus can be a 100 microsecond click for neurodiagnosis or a tone burst. Rate is typically set to 7.1 per second. For infants, you can acquire at slower rates of 0.9 per second or 1.9 per second. Adults can be tested up to 9.9 per second. Polarity is typically alternating in order to reduce stimulus artifact. Transducers, as mentioned earlier, are usually insert earphones or sound field. Starting intensity is typically around 70 dB NHL. Masking is 50 dB SPL only if the stimulus exceeds 70 dB NHL. Filters can be 10 to 1500 Hz or 30 to 300 Hz. Notch filter is typically turned off unless it is necessary to activate due to power line noise. The gain or amplification can be set to 75K or 100K. The overall analysis time window is usually set to 100 milliseconds. Sweep count is about 1,000. For two-channel systems, you can set the mode to both and acquire both ipsilateral and contralateral responses. Otherwise, ipsilateral responses may suffice. The recommended electrode montage is as follows. Reference inverting negative inputs are connected to the earlobes A1 and A2 for left and right ear respectively. The earlobes can also be linked with a linking cable for laterality. The non-inverting positive inputs are connected to CZ, typically connected to a two-channel system via shared Y adapter between both right and left channels. These non-inverting positive inputs can also be connected to C3 or T3 for left hemisphere testing, connected to the left channel, and C4 or T4 for right hemisphere testing, connected to the right channel. The right connection can be made to the forehead nasion or FPZ site. Patients should be awake and attentive to the stimulus during testing. Impedance should be less than 5 kiloohms with minimal differences across electrodes. Once the acquisition parameters are loaded and the electrode montage is set up and the patient is connected, please proceed to acquire 2 to 4 recordings by selecting Acquire. Here you see MLR IPSI and contralateral responses using 2 sets of bandpass filters, 10 to 1500 Hz and 30 to 300 Hz. The MLR occurs approximately 12 to 75 milliseconds after the stimulus onset. NA typically occurs between 12 and 21 milliseconds. PA occurs between 21 and 38 milliseconds. NB occurs just after PA, and PB occurs after NB at approximately 50 milliseconds. NA and PA are used clinically for presence and absence assessment, as well as latency and amplitude analysis. Monitoring of the PB, or the P50 response, provides evidence of maturation and has been shown as delayed in hearing loss individuals. It can also be used in discrimination gap detection assessments. Research has shown a significant difference in MLRs between learning disabled children and normal hearing controls. Case studies have also been presented in the literature of children with normal ABRs but absent MLRs. With SmartEP, you can also acquire the MLR 40 Hz steady-state response using a special 40 Hz response stimulus file, delivered at 10 per second rate for general threshold detection. Note, the stimulus file should be calibrated before use. Next, SmartEP also offers the P50 gap paradigm research use only modality. The P50 response is used to measure sensory gating, or the reduced neurophysiological response to redundant stimuli. P50 is an auditory evoked potential occurring approximately 50 milliseconds after the onset of a stimulus. The P50 module is used to record responses to 2 equal-length consecutive stimuli, typically an auditory paired 100 microsecond click, to observe the effect of P50 suppression. These stimuli have 2 different interstimulus intervals, or ISI, of separation between them as shown in the graph. The second sound is considered redundant, and so a typical control showing normal sensory gating will produce a reduced response in wave amplitude to the second click. Here is a list of general information regarding the acquisition of the P50 response. The most commonly used ISI values are 500 and 3000 milliseconds. Our observations show that ISI2 intervals of 3000 milliseconds can produce repeatable results with minimal subject discomfort and with a reasonable recording duration. Filtering with high pass set to 1 Hz, low pass set to 100 Hz, and a gain set to 100K should be appropriate for acquisition of P50. Patients should be awake and alert. Due to the required long ISI values, it may be beneficial to acquire sweeps in small batches and then add the recordings into a grand average post-acquisition. Research has found that an abnormal P50 suppression can be a biomarker for several disorders or pathologies and cognitive processes. Now let's discuss the Cortical Auditory Evoked Potential late latency response. Acquisition is performed using the SmartEP auditory LLR modality. As with the AMLR, you can activate the mode using the options in the protocol menu or by loading an LLR settings file. Shown on this slide are the recommended settings for acquisition of LLR responses. The stimulus is typically a 100 microsecond click or long duration, for example, 40 milliseconds, tone burst, and low frequency, mid frequency, and high frequency speech tokens. The rate can vary from 0.7 per second to 1.9 per second. Polarity is alternating. Transducers are typically insert earphones or sound field. Intensities are typically 75, 65, and 55 dB NHLs. Masking of 50 dB is only used if the stimulus exceeds 70 dB NHL. High-pass filters can be set to 0.1 Hz and 1 Hz. The low-pass filter can be set to 30 Hz or 100 Hz. Note that you can apply offline filtering to acquired responses. Notch filter should be turned off unless there is excessive line noise present. Regarding gain or amplification, since these are larger responses, you do not typically need the larger gain value of 100K. This 50K or 75K may suffice. Artifact rejection is set per patient and is influenced by the eye blink artifact. Using one channel as an ocular channel to measure the eye blink artifact is recommended. The overall analysis time window would be 512 milliseconds to 600 milliseconds and will depend on stimulus duration. Users can plot pre-stimulus for baseline amplitude measurements. Sweeps are typically set to 256, and mode is set to acquire ipsilateral responses. Here is a CAEP LLR response to a 2000 Hz stimulus presented via air conduction insert earphones at 70 dB NHL. Here is an example of a CAEP LLR response to a 40 millisecond DA speech token stimulus presented via air conduction insert earphones at 75 dB SPL. IHS also offers a low, a mid, and 2 high-frequency consonant speech tokens for CAEP testing. The M, low-frequency sound, the G, mid-frequency sound, and the 2 T, and S, high-frequency sounds. These speech tokens are calibrated for ER3C, ER3A insert earphones from the factory. The stimulus files can be calibrated by the user for any stimulator transducer used, for example, for use in Soundfield. IHS offers pre-programmed settings files for each of these speech tokens. Shown on this slide are the speech token spectral components and respective sample LLR recordings or responses to each sound presented via air conduction at 75 dB SPL. Now let's move on to the P300 MMN modality. P300 and mismatched negativity responses are potential differences generated when a patient is stimulated with a stimulus train containing a frequently occurring common stimuli and an infrequent, oddball, rare, deviant stimuli. The potential difference originates in the auditory cortex and can be recorded by averaging the acquired signal over a specified period of time. An ideal P300 recording will contain one large peak at around 300 milliseconds in response to stimulation. The amplitude of the peak is inversely related to the level of expectation for the odd stimulus, and the latency is related to the ratio of standard to deviant stimuli. An ideal MMN recording will contain a difference between the response to standard stimulus and the response to the deviant stimulus, which can be observed in the 100 to 200 millisecond region. To acquire the P300MMN response, access the add-on modality Auditory P300MMN from the protocol menu. When in this mode, the intensity button of the SmartEP control panel will be replaced with a P300 setup button. This button opens a window where the testing paradigm can be defined. We will review this option shortly. But first, let's review artifact rejection. Using the standard AEP module yields rejections based solely on the artifact rejection amplitude level selected in the amplifier settings window. In versions prior to 5.53, the P300MMN module automatically rejects the common stimulus after the oddball rare stimulus is presented, because some researchers consider the common to be different than the standard common EP, as it occurs after a different stimulus. But we do offer our customers the option not to reject the common after the rare if their research calls for this. In versions prior to 5.53, this would require a renaming of the DSP out files. You can contact our support team for guidance. In version 5.53 or higher, you can choose whether to reject the common after the rare or not directly from the P300 setup screen. When acquiring P300s and other cortical potentials, you may want to monitor the iBlink artifact to see if it is influencing or affecting your response. You can set up one amplifier channel as your acquisition channel by designating the channel for the hemisphere you are testing, right or left, and set up the other channel as your iBlink monitoring channel by setting the designation to on. Here you see channel A set up as the test acquisition channel, while channel B is set up as the iBlink monitoring channel. Channel A is designated as the right channel, and the Electrode Montage is specified as A2, CZ, and FPZ, while channel B is simply designated as on, which means the device will acquire the iBlink response from that channel, and the Electrode Montage has been specified as I write positive, I write negative, and FPZ. If you are setting up right ear and hemisphere testing, channel A would be the test channel, and channel B would be the iBlink channel. If you are setting up left ear and hemisphere testing, channel A would be the iBlink channel, and channel B would be the test channel. Here's a P300MMN setup screen. Within this window, you can load up to 4 stimuli, specify the percentage of presentation for each stimuli, select the stimulation ear, sound output mode, and the acquisition channels. As a SmartEP version 5.31 or higher, you can check or uncheck the rejection of the common sweep after the odd directly from the setup screen. You can also specify a percentage of stimulus rate jitter. The jitter is an added delay to the interstimulus interval or ISI. The smallest ISI will correspond to the selected rate. The P300 module generates different triggers using the I/O port of the device. We have added an option to enter trigger out timing offset values in microseconds to the P300MMN setup screen. These values must be entered in 25 microsecond intervals. Trigger outs are generated at the 512th data point corresponding to time 0. In the latest version of the software, an offset value may now be selected to generate the trigger ahead or after the 512th data point. This option is primarily intended to synchronize videos with sound output, but may be used for other research applications. We have also added a feature to implement different special 50/50 sequences if you check the special 2-buffer 50/50 mode. This will either generate a common odd sequence when the reject common after odd is not active or selected, or it will generate a common odd sequence when the reject common after odd is active or checked selected. When the special 2-buffer 50/50 mode is not selected, but the user enters a 50/50% presentation into the setup module, the system will generate the corresponding random sequence, which will likely include successive odd presentations. Once the oddball paradigm is defined in the P300 setup screen, you can link it to the standard acquisition parameters and amplifier settings found on the main control panel and amplifier settings window using the Save Settings feature. In version 5.53 and higher, when you select Save Settings to save the settings file, this will automatically save the P300 MMN parameter setup file with the same file name. Click Acquire to record the P300 response. Note, the patient should be alert, staring at a target, minimizing any eye blinks, and should mentally count the oddball stimuli during the test. Inform the patient that they will be asked how many oddball stimuli they heard at the end of the test. This will motivate the patient to keep attention on the task. Some clinicians have used a push button or retractable pen and have the patient gently press down on the push button or pen each time they hear and count an oddball stimulus being presented. This helps the patient keep alert. It is important that if something like this is used, that it does not introduce unnecessary EMG artifacts into the recording. Here, on the left side of the screen, you will see the oddball rare responses tagged as buffer 1, which shows the P300 peak. And on the right side, we see the common responses tagged as buffer 0. To derive an MMN response, simply set the process menu subtraction mode to microvolt weighted, and then activate the grand average oddball response, followed by the grand average common response, and then select the option to subtract two selected recordings. This will result in a derived MMN response, which you can save as a new data file and mark its area amplitude. Now let's discuss Acoustic Change Complex, or ACCs. For ACC acquisition paradigms, you can use the P300 MMN module. ACCs are the long latency potentials P1, N1, P2 recorded after changes in the stimulus. The stimuli can be, for example, syllables or tones, where some parameter of the same, such as frequency, intensity, ISI, or another parameter is changed. The goal is to study the auditory perception of patients. Therefore, to register these ACCs, you would need to determine the type of stimuli you wish to use and the changes in the stimulus you want to implement. Then create these stimuli either using a third-party audio editing program like Audacity or using the IHS stimulus generation module. If you generate a WAV file from an external audio editing software, note that it will need to be converted using our stimulus conversion utility to convert the WAV file to STIM format. All stimuli generated will need to be calibrated using the stimulus calibration file utility. For this type of testing, reject common after rare is not checked or selected. Then your speech tokens are loaded and the stimulus presentation percentages are set, and the setup module is configured. Here you can see sample ACC recordings based on the setup configured. You can also acquire ACCs using the Advanced Auditory Research Module LLR modality. Concatenated tones can be created using the IHS Stimulus Generation module. The concatenated tones can be loaded along with a speech token into the Advanced Auditory Research module as shown here. Here are the ACC responses for this type of setup. This completes the review of the SmartEP Cortical Evoked Potentials options. Thank you for watching this video. For more information on the SmartEP Cortical options, please contact our sales team at sales@ihsys.com or visit our website at www.ihsys.com. If you have any technical questions or suggestions, please contact our support team at support@ihsys.com.